So that's basically what we were last time. Okay, so the lesson we left it last time is how many duplication we should run to have a good estimation of our confidence interval. Our confidence interval is in the forms of we have the let me plot it here. This is our confidence interval. Okay, this is the average. Okay, so half of our confidence interval is calculated by this equation. Half width of our confidence interval is calculated by this equation. Okay, so a good estimation of our confidence interval means our certainty level, our confidence level should be very high. Okay, so we usually use like 95% confidence level, right? The level 95% confidence level is better than 90% confidence interval is better than 80% confidence level. Okay, so the higher the confidence level, the better. Right now, and then the good estimation also refer to the width of our confidence, like the estimation range. Like if we give an estimation which is too wide, means that our precision is not is very low. Okay, our estimation, our prediction is too wide. It will be not useful. So a good estimation also means that our confidence range, our confidence interval should be small enough, should be precise enough. And how precise it is depends on your expectation. Okay, but too wide is not helpful at all. All right, in short, a good estimation refers to both. Firstly, we have a high confidence level, and secondly, we have a high precision in our estimation. All right, now we take this example. Okay, so let's say we are simulating this recycle product system. Okay, so this is our product. This is our product, the original product. Okay, and then they are used by our customer. They are sold to the customer and used by the customer. All right. So after some time, some of the product still good, still okay, and some like got some defective part in our product. It is a defective product. Okay, and so it cannot be used anymore, and then it was returned to the, let's say, to the its original company. Okay, and there they will dismantle the product, right, to take the good parts which still can be usable, and the bad part, one will be disposed. Right. So the company, let's say, will recollect many recycled products like this one, and then try to sort out the reusable part. Okay. And then these are the component that still be reusable. Okay, and then they will form a recycle kits, and then rework it and make it a new product again, and then introduce it into the market again. Right? Interesting. Okay, so let's say for this system, what we are interested in. Okay, let's say we are interested in the cycle time, right, of each unit here. Let's say the cycle time of each product here, one cycle like that, how long it takes. Okay, and it could be a random variable. It will be different for different product. Okay, so this is what we get from the simulation result. All right, besides this example, besides of the time, the recycle time, we're also interested in the recycle cost. Okay, so we will look at the recycle cost. The recycle cost is also a variable because like sometimes maybe a product have two defective parts, sometimes a product have three defective parts, and so the cost of dismantle it will be different. Okay, so we will look at the cost, the remanufacture unit cost. Okay, so here we will run the simulation for many times, and one duplication we will run for different product here. Okay, and we get the remanufacturer unit cost for different duplication. Okay, we got the average, the standard deviation. Okay, this one is the upper limit and the lower limit of our confidence interval. So within alpha 0.05, 0.05 alpha equal to 0.05 means our confidence interval would be, our confidence level would be 95%. Okay. This is our alpha. This is alpha over 2. Alpha over 2. Alpha is the rejection region, the probability for rejection. So this will be our confidence interval. If alpha is 0.05, so this one would be 95%. We are 95% confidence that the average of the recycle cost is between 1.595 and 1.675. Okay, 1.595 and 1.675. Now, this is our estimation of the average remanufacturer unit cost. Is it a good estimation? Is it a good estimation? Well, let's say we want to increase the precision. Okay, like from 1.595 and 1.675. We still want to increase the precision or reduce this range. Okay, increase the precision or reduce this range. It means that we want to narrow down this. Okay. We want to narrow down this estimation, make it more precise. So you see that when we reduce the confidence interval, the alpha become increasing, right? This one, our alpha increasing. Or our confidence level reduced. Now the 95% would be reduced. We can only, if we want to increase the precision by reduce the interval, okay, then our level will naturally reduce, automatically reduce. Okay, so that is kind of trade-off. So let's say we try to change our confidence limit from 95% to 80% and see how precise we can estimate. All right. So when we go back to this equation, okay, you look at this one. For the same number of replication, for the same R, okay, if we reduce, if we want this one reduce, okay, the alpha need to be reduced. Okay, the alpha reduced, and the t, this t need to be reduced. Okay, the t value will be reduced when you have alpha. Let me see. Oh, sorry, when we have alpha increase. Sorry, the t will reduce if you have alpha increase. Okay, so we go back to this. All right, so the t value, you check the t value. This is the t value when alpha equal to 0.05. Okay, and we have 20 replications, so the degree of freedom is 19. Okay, now we will change the alpha. If our confidence level from 95% to 80%, it means that our alpha will change from 5% to 20%. Okay, so you have to look for the new t value here. Okay, alpha equal to 0.2 or 20%, and still we have the same number of replication, 19, okay, and we got the new value of t for the half-width calculation. Okay, you see that when alpha increase, the t value will reduce. And then if we plug in our t value again for the new confidence level, we will have the new half-width estimation, okay, which is very, very narrow compared to the previous one. This is the previous one, and this is the new one. For the new alpha, for the new confidence level, we are able to give the estimation of the cost ranging from 1.609 to 1.660. Okay, this is good, but we are less confident. For the new estimation, we are only at 80% confidence compared to the 95% confidence previously. This one. Okay, so this is the trade-off. So how do we solve this trade-off? Like we want to have both high confidence level and high precision, okay, or narrow. range of estimate. This is what we want, right? We want high confidence level. 95% confidence level is better than 80% confidence level. And we want narrow range of estimate. Okay. The narrower our estimation, the better. Right? But it seems that we cannot achieve that for the same number of replication. Okay, if we fix this one, if we want to have high confidence level, this one is small, we want this one small, okay, and automatically this one would be large. All right, so the only way here is to set a certain confidence level that we want. Okay, set an alpha, we will fix alpha. Okay, and then we will vary the number of replication, this one. All right, so let's say we want the confidence level at 95% or alpha is 0.05. So let's fix it. All right, now we will try to reduce this one. We will try to reduce this half width by changing the number of replication here. And we should increase the number of replication in order to reduce the half width. All right, so how many replications we need to run here depends on how precise you want for your confidence interval. Okay? Okay, so we can estimate that one. Let's say we expect that our estimation should be smaller than certain epsilon. Okay, we have this number in mind. This is our expected error. Larger than this epsilon it should be, it will be too rough. All right, so we want our output performance estimation should be within this epsilon to be meaningful. All right, and so this epsilon we can estimate our half width confidence interval using this equation and set it smaller than this value. Okay, the confidence interval, the half width of the confidence interval, this is a half width. All right, we will set it smaller than the epsilon that we want. Right, so a simple math, we will get this number of replication. This is the minimum replication we need to run in order to have our half width of confidence smaller than the epsilon value that we want. All right, so this is the number of replication, the smallest number of replication we need to run in order to have our half width confidence intervals smaller than the error that we want. Okay, but what is the problem here? Okay, we can replace the sign by equal, right? But set the number, the minimum replication we need to run. So can we use this equation to know the number of replication? This is straightforward. Now, well, you only need to find the value of this one. Okay, and then that is our replication. But let's look at this equation. How do we compute this one? Okay, epsilon we know epsilon because this is the value we want. So we know this one. It is given. Epsilon is given. But how about this one? What is the S here? What is the S here? This is the variance, right? The variance from our replication in our simulation. So if you run it 20 times, you have to calculate the variance from the 20 replication of our simulation. But what? It means that this one depends on the number of replication we run. Okay, we want to know R. If we want to know R, we need to calculate S. But in order to calculate S, we need to have R first. All right. So if we want to know R, we need to have S, the variance. But in order to calculate S, the variance, we need to run first. And when we run, you have to know how many replications you run in order to compute the variance. All right, so it's like a loop here. So we have a problem here. Right? Can you imagine that? Okay, let's look at this one. Okay, this is the number of replication we run. And this is R time, we run it R time. And from this R time, we calculate the variance. Okay, the variance here. So we need to know R first. We need to decide how many replication first. And then we run and we got the result, then we can calculate S. All right, so it's not quite straightforward. Okay, what else? Okay, so we have S already depend on R here. How about the T alpha, the T value? How do we find the critical value here? All right, we need to decide the alpha level, which is okay. Let's choose it 5%. But the T value is found in the T distribution and it has a degree of freedom. The degree of freedom here also depends on number of replication. It is R minus 1. Okay, so again, the T value here also depends on R. So now that is like almost impossible for us to calculate R from this equation, right? Okay, so what should we do then? All right, so this is what we are going to do. It's not a straightforward equation, so we have to run a few times. All right, it's an iterative calculation process to come up with the R value to solve this equation, right? So firstly, what we do firstly, we don't know how many replications we should run. We just run a few times first. Just run an initial a few replication first. Whatever number that we think that is appropriate, that our time is can afford. Okay, so we will run an R0 times first. Let's say we run it 10 times first and see how. All right, so when we decide to run an initial number of replication first, we got the result. Okay, let's say we set it 10 times. We run 10 times first. We don't know what is the good one. Just try number. So run 10 times first. So after these initial runs, we would be able to calculate the variance from the first few initial runs. All right, okay. So we will take this value from our initial R0 runs. Now for the t value, to make it simple, we can approximate it with the normal distribution. Okay, you know that the t distribution is very close to the normal distribution when the sample size is large. Okay, so this is just the first estimation. So we know that we still have to try many more. So let's make it simple by using the z value of the normal distribution instead of the t value of the t distribution. Right, they're not the same, but we know that they are close enough for us just to take the value for estimation. All right, so we replace the t here for the z. Why we want to replace t for z? See, in t distribution, we need to know the degree freedom here. Okay, and that's make it very complicated. So that's why we want to replace t by z. Just want to estimate. And in normal distribution, we don't have any degree freedom there. Okay, so somehow we can skip this one. All right, so the second step, we will recalculate R, our new R again. Right. And in this new R, we will use a Z instead of T. All right, our R1, we use a Z instead of T value. We will use the S0 at the beginning from our first initial runs here. Okay. And divide it by S0, okay? Square. Okay, so so we will have the new one and we calculate the new R1 value. And this time our R1, okay, our R1 would be different with the first time. Right, and of course it would be larger than the first time. Right, it will be larger than the first time. All right, then we have to run additional runs, R minus R0. Right, and we just like keep repeating this process until 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 they are very close to the first one. All right, so this is one way for us to decide the number of runs for a given design precision Excel. Okay, so we can take this example. Okay, so let's say we are looking at the resource utilization from our simulation. Okay, resource utilization. And we want to estimate this output within plus or minus 0.04. Okay, you know, resource utilization is in the percentage. So we want to give an estimation that's the erg just within 4%. All right, and with a probability 95%. Okay, so we want our prediction with a very high confidence interval level. Right, so in this case, our overall criterion echelon would be 0.04. So it would be 0.04 here. Oops, sorry. Oh, okay, let's try again. Our overall echelon will be 0.04. And our confidence level will be 95%. Or our alpha would be 5%. Right, so now we want to see how many replications we need to run in order to get this. In order to have our confidence interval within this 0.04 and with the confidence level 95%. Okay, so we don't know, we just run first. Now let's say initial, our sample size is 4. We just run 4 times. And then we would have 4 results, 4 values of resource utilization. And we calculate, we estimate the variance is this large from that 4 result. Okay, and then we will calculate again value of number replication using this equation. We use Z value of the normal distribution, standard normal distribution instead of the T. Okay, we use the variance that we just get from the 4 replication. Okay, and this is our error, expected error. Okay, and we got the new R. We should run about more than 12 times. Okay, so it should be more than 12 times. But exactly how many we have not shown yet. Okay, so if we want to show a particular, a specific value of R, then we have to continue. Okay, we will try, okay, let's set R equal to 13. Okay, 13, and see how. In your simulation, if you already done 4 times, then you only need to run 9 times more. Okay, but it's more convenient if you just set 13 times in arena. Okay, instead of say the 4 initial result, run 9 more replications, you just set it 13 times in arena. It's much faster. Okay, so we set a new R here. And this time, let's say you want to be more precise. Then the first trying, then you use the T value. Okay, and you got the T value for the 13 times is 2.18. Okay, and we use this equation. All right. Remember, when you run the new 13 times here, you will have the new S as well. Okay, right? You plug in the S and the new T, the new S, and we got the new triplication is about more than 15. All right, more than 15. Well, you can try 14 and 15, but if you try 15, let's see how. If you try 15 here, you got a new number here, the new R, which is 14.83, which is very close to the one here. Okay, this is the first R we try, and this one is the new R we get. As long as we have these two are very close, then we reach the solution. All right, so in this time, we can stop the fitting multiplication. We find that these two are quite close. Right, so R equal to 15 is our specific number multiplication we need to run in order to satisfy this requirement. Okay, now can we do faster than this? Wow, we also can. Let's look at this equation again. All right, we see that this is our R, right? Right, we can do a very quick estimation. Let's say we have some R. This is a number of replication we want to know. Okay, and let's replace it with replace the t with z value. Okay. All right, and let's assume that the variance doesn't change much. Okay, and let's assume that the variance doesn't change much. Then we will have the different epsilon here. Okay, let me go back to the previous slide. Okay, maybe this one is better. All right, let's try this one. Let's say we set this equation equal to our epsilon. The first half is here. All right, and we try a different replication here. The new one, let's try is hi. Hi here. Okay, this one we will replace it with z. So this one also equal to z. Okay, and is si divided by ri. All right, so for different duplication, we would have different half width of confidence. All right, and we will simplify the t by the z, and let's assume that the variance doesn't change much. Okay, so we can simplify. We take the ratio of these two. What we have here, this one we can simplify. We assume that this doesn't change much. So what do we have at the end? We have this ratio. Equal to the square root of Ri over, right? Okay. Put it another way, we would have the Ri equal to multiply with square. Right? Okay, so how can we use this equation? Right. So the R0 is the initial replication that you run, and H0 is the initial half-width that you have. So what do you want here? The HI is what you want here. So let's say you want epsilon, you want the half-width, you want to the half-width equal to epsilon. This is our design precision. So we will set this one epsilon, and we will see, estimate how many replications we have here, the Ri here. If the half width is set equal to epsilon. All right, so basically you need to run more replication, which is equal to the ratio of the initial half width with the design precision in square. This is a very rough estimation. Let's try this one with our example. Okay, let's clear this. Okay, so let's try this one. Can you try this one on your own? Okay, so what is our H note? What is our initial half width if we run for triplication? Can you calculate this one? Can you? All right, so it would be equal to Z multiplied with how many? Our S, right? Divide by the number of replication. So our Z is 1.96. 1.96. And our S here, you have the value here. All right, you take this value here. And you divide it by square root of 4. What do you have here? Can anyone try it? I don't have the calculator here. Can anyone try it and give me a number? Okay, I'm waiting for you to give me a number of our initial half width before replication. Okay, thanks, man. We have 0.005. Is it correct? Is it correct? That is a very small one. Okay, let's me try. Okay, we have 0.005. Oh, all right. So everyone got 0.005, is it? Let me have a look at this one. Is it correct? Oh yeah, it's correct. no. Let me try. 0.005 divided by square 4 divided by 2. Okay, let me try check this again. Okay, so divided by 2, and this is 1.96. Yeah, it's about that. All right. So if we use the equation, what do we have here? Our H0 would be equal to 0.005. Right. But okay, and what we want here, we want our H0 should be 0.04. Okay, so our HI would be 0.04, smaller than 0.0. Oh, I'm sorry, you got here. Oh, in this case, then the estimation using this equation is not good because it's too rough. Right. Right now we have our heteron here is already very, very small compared to what we want here. All right, so in this case, we are more than our expectation. So using this equation actually sometimes is not good enough. In the case when our first half is already smaller than our criterion, then we have to check this. Is this true? All right, so in this case, well, I give you a bad example already because the initial half width is already smaller than this one. All right, but wow, you can try another example with this equation. Okay, take the ratio of this one and just look at the ratio with the number of publication and use Z replaced by T. Okay, in this example, it is not a good example for that way. All right, because the initial one already seems to be smaller than our expectation. All right, okay. Now let's see. We have a few questions here. Like, how can we define the good error in this case? The good error in this case is from our practical point of view. How do we, of the user of the system? Okay, it's just like the practical error that I mentioned in the validation lesson. All right, so it's very subjective. It depends on the user. It depends on the manager of the system. All right, so let's say I usually use the waiting time for the examples. All right, so let's say for the real system, the customer usually have to wait an average time of 45 minutes. 45 minutes. So if your simulation result give the estimation of the waiting time, the confidence interval. All right, let me put it here so that we can. All right, okay, let me put it on the screen. Let's say in the real system, the waiting time, the waiting time is about 45 minutes. Okay, and then in our simulation, we estimate the waiting time, the average waiting time, and the range we estimate here. The half width is about 30 minutes plus a 30 minutes precision. Then it would be too wide. Okay, and the manager say, wow, I cannot accept it. Okay, your confidence interval is plus or minus 30 minutes. It's too last because on average, the customer already wait 45 minutes. So I expect your simulation result should give me the estimation plus or minus the accuracy should be around 5 minutes. Right? The manager asked that if you give me an estimation plus the average waiting time in your simulation is also 14 minutes, but plus or minus 30 minutes. Wow, it means that the output of our simulation may vary from 10 minutes to 70 minutes. The confidence interval is too wide. All right. So the manager say, I only allow you to have to give me an estimation with the error about plus or minus 5 minutes. All right. So in that case, you have to run your simulation how many times in order to give the confidence interval within 5 minutes only. Right. So the good error in this case is a practical point of view. Okay, so if it is time, I give you maybe plus or 5 minutes, but if it is the money, okay, and you for money 100,000 dong may be very small. All right, maybe you allow it's 1 million dong or 500,000 dong. It depends on the user of the system. What is the value meaningful to them? So you have to decide that. Right? It depends on the context, it depends on the system, it depends on the output performance you are looking at. Okay, all right. Okay, good question, man. Actually, that is a very good question. All right. Any other question? All right. If not, then we will going on. Okay, so let me introduce a little bit about the steady state simulation. Okay, so last time I already explained to you there are two types of system. All right, so the system by nature may have the starting point and stopping point. A system may like by nature is seem to run continuously, and what we want to evaluate the performance of a system which run continuously is in its stable state, right? Because we don't know, it doesn't have, let's say it's like restaurant. When we open the restaurant at the beginning, we have few customer, then the customer increasing, and then the customer reduce, and the number of customer may vary with time in a terminating simulation. But in a steady state simulation, the simulation just run continuously, and we want to look at the performance where uh, in its normal state, in its usual state. All right. So whether we treat the system as a steady state simulation or terminating simulation actually not only depends on the nature of the system, but also depends on our simulation objective. Okay. When we say steady state simulation, we mean that we need to run the simulation for a long time enough so that we can achieve the stable state of certain performance output. All right. So for example, in the hospital, you may want to run the simulation for the peak hour, or you want to run the simulation long enough until the waiting time of the patient almost doesn't change. Okay. If we look at the simulation as the terminating simulation, you will see the patient arrive in the very early morning, no, almost doesn't have to wait at all. Okay, but when the hospital already at its steady state, almost uh, any patient arrive have to wait about the same time, right? We look at the running of the factory at the, let's say, at the first shift of the week. Then we see a lot of fluctuation in the inventory level. But throughout the week, when the production lines already achieve a stable state, the inventory level almost remain the same. Okay. So we want to run our simulation uh, when it reaches the steady state and look at its performance output. So the point here is how to decide the steady state of the system, how to decide the length of our simulation so that we can take the steady state output. Okay, we will answer this one. All right, so we look at how we set up our simulation. Okay, well, actually we have a few actually we have two main ways to do this one. Okay, let's say we plot this here. So we look at the customer in the system. This is time, okay, and this is the number of customer. At the beginning, we don't have any customer, then it's increasing, it's stable. Okay, what we want to look at is here. All right, now the first method is we will initialize a simulation in a state that is quite representative for the steady state. So we can start our simulation at time 0 here. This is our time 0, the simulation plot at time 0. But we set the initial inventory level or the initial customer at time t0, or let's say we set the initial component fails in our system. All right, and this initial one somehow represent for the steady state. We have to set it at the beginning. And how do we do that? How do we know this initial inventory level or initial customer in queue? Yeah. All right. Wow. We have to collect the data from the real system. All right. So let's say for a hospital, you have to go there and observe when the hospital seems to be stabilized, like every customer arrive have to wait around the same time, for example, and you look at like in that system, like how many patients already there, for example. All right, so we have to set the initial condition here by collecting the data on the existing system, right? However, the more common method here is the second one. We just run our simulation as usual. Okay, so we run our simulation from here. And we accept that when our simulation starts, everything like nothing in our system. Okay, no customer, machine is idle, no inventory. Just run as usual. No setting initial condition here. But we will allow it run. And we will divide our simulation run into two phases. The initial phase, this one we call the initialization phase. I have the pictures here. Okay. Right, the initial phase here, the initialization phase, where our graph is like this one. Okay, and the second phase we call a data collection phase. It means that we will ask the software just let the simulation run for a certain initialization time, but do not collect any statistical data here. All right, and start to collect the output data first for this period. All right, so in Arena, it would be equivalent, the initialization phase would be equivalent to the warm up time in the run setup. Okay, this one is the warm up time. You remember in the run setup in the Arena, you have to tell like how many replications you want, then how many, how long for one replication, and whether you want warm up time or not. By default, the warm up time, you tell Arena that do not collect any data during this time and only start to collect data, and all the result that we read in the report is from the data collected in this phase. Right. Now, the problem now is we have to decide what is the warm-up period. All right. After we define the warm-up period, then you just key in Arena. The rest will be easy. Okay. So, all right, we will, okay, I will do more to you later. Now let's try a little bit longer. Okay, so we will learn how to identify the state in theory first, and then I show you how to do it in Arena later. Okay. All right. So let me have another slide here. Okay, let's me plot here. Okay. Let's say we want to look at say the cycle time. Okay, the cycle time of the entity, or the time in system of our entity. And then this is what the data that we get from the simulation. We will run it a few times, a few replication. Okay, this is the replication we have for the first time. Okay, we have the first entity arrive. Okay, so we will have y1. Okay, so this is the time in system of the first entity for the first verification. And then we would have, and then we have this first, the time in system, the second entity of the first verification. And let's say we would have the first verification and N1 entity. All right. And so the second verification, and then we have the R replication. We would have R, Y, R1, Y, R2, and Y, I'm sorry, yes, Y, N. All right. Normally, we will take the average of within duplication, right? We will take the average of within duplication. YR is the average of within duplication. But for identifying the steady state, we want to monitor how the variable, the output vary with time. So in this case, we will try, we will calculate the ensemble average. Another way, we don't do this, we don't look at this one, we will look at this. All right, so what is usually the average waiting time, time in system of the first entity after R replication? Okay, so the first one, what is the average time in system of the second entity that enter our system? All right, and then what we will plot this one on a graph. Okay, we will plot this on a graph and see when it's reached the stable state. Okay, so we will observe how the average through all the replication. All right, so this one will be our y, see, y2, and so on. All right, and we just observe by eyes. It's quite subjective again to see when our system reaches the stable state. Right. So in short, instead of plotting all of these, and it's made us very difficult to observe, you can plot the average like this one. All right, so that is what we call the ensemble average. Oh, it's so terrible. Okay, all right, this one we call ensemble average. We will plot the average of the output across duplication. Okay, if we plot the average across duplication, the plot will be much smoother than we plot for individual duplication. Okay, so each point here actually is the average. The first entity, the average of the first entity through 10 duplication, for example, and then the average of the second entity throughout the 10 duplication, and so on. Okay, and we can even achieve a smoother graph for identifying the steady state by plotting the moving average instead of the ensemble average. Okay, the moving average is like this. Right, just now, like we have entity 1 to n entity, for example, all right? And then one, the verification 1 to 10, for example. That here we would have 1, 2, 3, and so on. So we will plot the moving average instead of plotting individual like this one. We will plot the moving average. Okay, the average of this one, and then the average of this, and then the average of this. Okay, that's what we call moving average. Okay, let's take example. Let's say if we have n equal to 1. Okay, so this equation becomes the average of j entity would be equal to 1 over 3. All right, and I would run from j minus 1 to j plus 1. Mean that we will take the average of j minus 1 plus j plus 1. Okay, and our j would be the entity. So basically we move like this one, like what I'm showing you here. Okay, move by having 3 entities like this. If n equal to 5, sorry, n equal to 2, we would have divided by 5. It is the average of y I equal to j minus 2 plus j minus 1 plus j, okay, j plus 1 and j plus 2. Okay, so it's the average of 5, right? Okay, so it's still the ensemble average, but we move by 5 entities. Okay, and when we have, because the reason we are doing that is to smoother our plot. If we have a very fluctuate plot like this one, then it's quite hard for us to estimate, to identify the state. But if we are able to smoother this one, like the graph we have here, then it could be easier for us to see when the output become more stable. All right. Okay, so this is one way to identify the state by using the ensemble average. All right, everyone. Okay, we take a break here. Okay, we take a 10 minutes break here. If you have any question, you just leave on the chat box and then I will answer after the break. Okay, thank you, class.
Recording stopped.
Hello, class. I'm back. Are you there? Hello. All right. Okay, Hugh. Okay. How about others? Okay, come. All right, let's continue. I'm sorry, class. I just checked again the example that we just did. Yes, we have something wrong here. I typed the wrong number. So let's do it again. Okay. Right. Share the screen again. Okay. Hold up. Give me a second.
Recording in progress.
Okay. Let me try again here. Where are we? Okay, we are here. All right. I was careless in my slide here. Can you fix this one for me? In this example, the variance is 0.072. So when we scrape, it becomes 0.0518. So this one, we delete this one, all right? Okay, so we can try to calculate again the half width corresponding to 4 replication with this new value. All right. Just now we use the 0.0518, which is wrong. We already squared it. Okay, let's try it again. Here. My computer is hang. Give me a second to adjust it. Okay, let me try again if I can plot this here. Oh, all right, I can plot it here. Right. Okay, so let's try it here. Be equal to our z would be 1.96. And multiply with our s, which is 0.072. All right, and divided by our initial duplication, which is 4, square root of 4. So what is our half width of confidence? Have you calculated this one? Okay, I got the number 0.071. Thank you, Phương. Okay. Suddenly my computer become crazy. Okay, so we have 0.071 here. So if we take the ratio, we would have the new replication R2 will be equal to the number of replication, initial one, I mean 0 here, okay? And take the ratio of H1, or okay, let's say H2 divided by H0 and square. Okay, so in this case, we would have the first replication is 4 multiply with 0.07 and divided by our initial half width, which is, I'm sorry, this one is 0.04. This is our expected error, 0.04. Divided by, hold on, something wrong again. 0.04, that's right. Oh, I'm sorry, I'm wrong again, 0.2 here. Oops. All right, basically we will have the larger divided by the smaller. I cannot control it. Okay, give me a second. My pen doesn't work, so I'm quite clumsy. Sorry, class. Give me a second so that I'm logged in into my iPad and I can use my pen. Need to key in the information again, please.
Recording in progress.
Okay, now I can use my pen again. Okay. Oh, all right, I can use my iPad again. Oh, not this one. All right, so basically we would have the 4 multiply the new number of replication would be 4 divided by the old one, which is 0.07 divided by 0.04. I hope that you already figured it out by this time. Okay, sorry class. So we will get around 12.44. You get it? The new number of replication would be 12.44. Does everyone got this number? Okay, or less is larger than this one. Oh, okay, you got 12.55 is okay. So it's around that, I guess. So if we compare with this method, we got what? We got about 15 times. All right. And the equation we use is around 12 times. All right. So it still gives us a sum of um, close, quite close number. It starts from here. All right. So in actually, after we got this number, we still have to retry again, right? Because our Z value is a rough estimation for the T value. So let's say if you just need to have a rough quick and rough estimation, then you just use the ratio that I give you. All right, just take the ratio of the current half width that you run with the expected error that allow. Okay, square up them and multiply with the current replication. You already have a very close estimation for the required number of replication. Okay. All right. Thanks, Phương. Thanks a lot, Phương. All right, now we go back to our steady state simulation with the warm-up period. Okay, so after we identify our warm-up period, how is the output analysis? Okay, basically it would be the same with the terminating simulation after we already removing all the data from the warm-up period. Okay, so we call this method truncated replication. Okay. So still in the steady state simulation, we may need to run a few replications. Okay, so in the case that we run a number of replication, then we still can use the normal output analysis like the terminating conditions. It's like we need to use the across replication data, right, in order to use the classical statistical formula to estimate the half width of confidence interval. Okay, all right. The only difference is that we don't use the data in the warm-up period. All right, So this one we call truncated because we already cut off. Truncate means cut away. We already cut away the data during the warm-up period, and we only use the data during the steady state. So this one, all right, this one like we already deleted it. This one is in the warm-up period or the initialization phase. All right, cut away this one. And what we get the average from within the application is for the data collection phase. Okay, and after that for the output analysis, we just use the average across the application as the terminating simulation. Okay, this is the replication method for state simulation. We have to remove or we have to truncate all the data during the warm-up period. Okay, and this one is automatically done by in Arena when we define the warm-up period. It will automatically remove this one for us already. Okay, so this would be our average for each replication. After we already delete the observation during the warm-up period, this is within replication, the average for each replication, and this is the overall point estimate across the replication. So let's say we have R replication, we will take the average of R replication. All right, and then because for R replication, the R replication would be independent, so we can use this confidence interval estimate for R replication. All right, so as I told you, the only difference is that we have to remove the data during the warm-up period. Now this is a rough rule for us to estimate the warm-up period here. Okay, so if we look at n as the number of the entity, n is the number of entity per replication, n is the number of entity per replication, then for the warm-up period, it usually satisfy this condition. It's just a rough rule, okay? Right, let's say if you have like 100 entity per replication, you observe 100 entity enter during your simulation time, okay? And we will remove certain amount, certain number of entity during the warm-up period, that is D. Okay, so that D should be satisfied this condition, 10D, or we just move it, it could be N larger or equal than 11D. All right. Okay, it's just a rough rule. But if you look at the time length, we can either decide the warm-up period by the number of entity or by the time. Okay, if it is for the time, then we can use this rule of thumb. Okay, the time where we collect the simulation data, when we collect the statistic, should be larger, at least larger than 10 times of the warm-up period if we use the time. Okay, this is just a rough rule. I forget to put the reference here for you. I will look at the reference again and put it here for you. Actually, I need to put a reference here for you. All right. Okay, so this is the first method for us to analyze the output from the state-by-state simulation. Now we go to the second one. Okay, the first method we call truncated replication. It is usually used when we are able to identify the model warm-up and run lengths. Okay, and we can use the simple statistical analysis like the terminating simulation by looking at the across replication, the across truncated replication. We consider it's independent, and then we use the classical formula to calculate the confidence interval, so on. Now, in the case when we really don't know the warm-up time because it's too long, we cannot identify it. All right. So we have another alternative by making one really long run and there's no replication. Okay, so the normal state is set already really wrong. All right, and then we need to run a few replication, but now we met even longer time for one replication, but we only run one time. Okay, so what may be, what is the justification for doing that? So it's like instead of we will run, let's say we run 5 replication, 10 replication for 5 days. Okay, let's use the pen again. We have in the truncated replication, you may set 10 replication. And each replication 5 days. All right, so these 5 days may including 2 days warm up and 3 days for data collection. Okay, and these 5 days already considered long enough for steady run simulation. This is for truncated replication. Now for a batching single run method, we run only one replication, but for say 50 days. All right, so you can quickly observe that roughly the amount of time for simulation about the same. Okay, 10 replication 5 days and 1 replication 50 days. So the number of data we collect in total from this simulation more or less the same. Right. But we have the advantage in the batching single run here. The advantage is that it will be faster because like for if we only run one replication, then we only need to go through one time of warm up. All right, while for the truncated one, when we run 10 replication, you need to go through 10 times of warm up period. So it seems to take longer time for the truncated in that case. Okay, now, however, we have a statistical problem in doing the output analysis for batching single run. Okay, do you remember like the reason why we have to run many replications? Do you still remember the reason? We need independent data for using classic statistical formula to calculate the half width of confidence interval. You remember that? If within one replication, our output performance on a variable will dependent on one another. So we cannot use the normal statistical equation, right? That's why we need across replication. We need to run many replication, and each output of the replication will be independent from one another. All right. But now in the batching single run, we run only one replication. So we violate that rules. So how do we deal with that? Okay, how do we deal with the correlation among the data within one run? Okay, so the technique that we do here, and actually you are not required to do it here, you only need to understand what the software is doing here, is they will group the data in one long replication into batch. Okay, so like you have a very long replication, a very long run in one replication like this, a lot of data here, like equivalent to 10 replication of 5 days. But now it is 50 days, so a lot of data is here. Okay, there's certainly correlation among the data within one run. So the technique here is we group the data into batch. We group the data into batch like this one. Okay, and the batch here need to be large enough. It should be large enough. Okay, the reason is that we need a large batch size is that when we group a lot of data into a big batch like this one, it's like we take the sample, okay, and they will have a tendency to be independent from one another, okay, so they will be independent from one another. This one is proved statistically. People already try with the simulation and then group the data into batches. The larger batch, then the average of each batch will be independent from one another. So if we look at individual data like this one, they will highly correlated with one another. But if we group into batch and it's large enough, the batch will be independent from one another. Okay, so this is a technique for analyze the output of one single run with a very long time. Okay, so now each replication will be replaced by batch. So what Arena do? We no need to do this one. You only need to understand it since we are learning theory one. Okay, so Arena will automatically form the batch during the simulation. All right. So if you try different batch size, it has an algorithm and try different batch size. Okay. So at the end of the simulation, after many trying, it will come up with about from 20 to 40 batch, very big one, and it will automatically compute the 95% confidence interval with batch mean for us. Right. So it's okay that in Arena you choose one replication and a very long run. When you choose a long run enough, then in your Arena report, you still can get the 95% confidence interval, the half width of your performance output. And the way Arena come up with that one is through the batch mean. It's already automatically group the data into bars for us, all right, in a way that the bars are independent from one another. All right, it will calculate the number of bars and the size of bars that last enough so that they are independent. Okay, when many times you may see in ARENA report, it says that the hub width is insufficient. Okay, this happens when we don't have enough replication, or we run only one replication, but it's long enough. Okay, when we run one replication but not long enough, it doesn't have enough data to group into batch. Okay, and so that it cannot use the classical equation to calculate for us the confidence interval, calculate the half width of confidence interval. And so the report will show us only the average. All right, so there are two cases where you cannot see the half width result in your report. The first case is you run so few replications. Right. The second case is you run so few replication or even only one replication, but the length of the replication is not long enough. So it doesn't have enough data for it to compute. All right, to group into batch. Okay. All right, now I will show you quickly how to do this one in Arena. Okay, please give me a second. I need to connect with my other laptop.
Recording stopped.
I have an old laptop that just for running Arena. Because my current laptop is the Mark one, so it cannot run Arena. Yeah. Mm. Okay, I'm going to share with you. Uh, all right, so I will open the one example that we have done in our class about the manufacturing system.
Recording in progress.
Okay, hope you still remember this example. All right, this is the one. Okay, suppose that we want to run this system for steady state to evaluate the inventory levels of the system. Okay, so in our statistic, we will record the WIP of the system, the total WIP of the system. WIP is considered inventory level. Okay. All right, so this is our WIP. Right, the WIP, the number in system would be considered the time persistent. So in the statistic, we have to choose the time persistent. If you choose the wrong one, it will calculate wrongly. Remember, the time persistent, the average for time persistent is different with the average for the tally one. Okay, so we have to choose the correct type to get the correct result. Okay, and this is the one that we have to pay attention in the output file. Let's say at the beginning, we don't know how long we need to set for the warm up period, but we decide that we will decide the state based on the inventory level. Okay, so by monitoring the inventory level throughout the simulation, we would consider when is the stable one. And so we will base on that and we set the warm-up time. But right now we don't know the warm-up time, so we just run it first. And then we will look at the inventory level to decide later. Okay. Okay, so in order to monitor the inventory level, we need to export the inventory level data, because if we just look at the arena report at the end, we only see the summarized or the average and the hard width or and the maximum and the minimum. So this is the reason in the output file, you have to key in the name of the output file for later using. Okay, so in this case, I type in the total width history, and the extension of the file should be .dat. Okay, .dat. Okay, you can choose the directory you want to store this file. For example, I want this directory. All right, and later I will go to this directory to find this file. Okay, the purpose of this step is to determine the warm-up time. All right, and for the run setup, right now I don't know what is the warm-up time, so I just leave it here, and I will run for 5 days. Right, I know that the system, this factory run 5 days a week. Okay, so I just run it 5 days. Right. And then we try to determine where is which steady state by looking at the total width in the system. Okay, so let's run it. Five days and 10 duplications. All right, yes, we can see the result. Okay, so if we look at the category overview, we can see the summarized result for 10 duplication. Okay, and let's look at our total width. The total width for 10 duplication, each duplication 5 days is 15 units. This is the half width, this is the minimum and maximum value. All right, if you go to individual category, we will have the result for each duplication. So this is the average within first duplication, the average within the 10 duplication, the average within the second duplication, and so on. Okay, but this is just a summarized report. Now let us look at the output data file that we record of the total width. All right, and we're going to plot it using an application in Arena named Output Analyzer. All right, I'm going to share with you another screen. Okay, in order to open the Output Analyzer, it is not available here. Here you can only find the Input Analyzer and the Process Analyzer. If you want the Output Analyzer, you have to go outside. Okay, go to the program file, the one that where you install your Arena. Okay, my one is in program files. Okay, and it's in Rockwell software in Arena. And then we look for the output analyzer. All right, do you see this one, the output.exe? Okay, output.exe, this is another application of Arena. All right, I double click here. All right, so this is our output analyzer. Right, we can analyze all the statistic file that we can extract from Arena. So I will plot it in the graph. and I use the plot. Okay, and I will plot the data file that we just saved just now. All right, I will add. Right, do you still remember the name of it? Is total whip history dot dat. All right, and you can look at the time here. It just recorded recently at 3:47. We just run it. Okay, so I open this file. All right, so you can plot. We have 10 replications for that data file. If we plot only one replication, let's see how. All right, so this is the total width for the first replication. All right, can you identify the steady state from here? It's a little bit hard, right? Okay, now let's run all the 10, let's plot all the 10 replication. Oops, sorry. The same data file, okay, I have to select it and edit. Okay, and I choose all replication. Oh, all right. All right, we can have all the 10 replication here. All right, so okay, so this is the wow, this is the plot we have. Can you identify the steady state from here? Okay, frankly speaking, to me, it's also hard to look at this one, but it seems that for many replications, okay, let's zoom out it. It's somehow like let's say you see this one, a lot of fluctuations before 2000 minutes. All right, around that time. Okay, a lot of fluctuation around the 2000 minutes, and then it seems to be stable. Yeah. All right. So while we can choose to for the warm up around this time. Okay, let's say, but this is really quite subjective if we look like this one. All right, but let's choose our warm up time is for around 2000 hours for around this one. Okay, okay, around this time it's about 2 days warm up time. All right. The theory that we learned just now, it would be much better. The plot here would be smoother if we use the ensemble average. The ensemble average means we don't look at individual replication like this one, but we set the average across replication. Okay, so for each one like this one, we will take the average replication, but I still cannot find where Arena give us the ensemble average, like what we learned. Okay, so perhaps if we want to do that, we have to plot by ourselves, by exporting the data and plot by ourselves the ensemble average to get a smoother one. Right now, I cannot find any function in Arena to do that, but just plot individual replication like that and using our eyeball to detect the warm-up length. All right, so okay, so maybe we just try the available tool that we have up to now. Okay, so this is one way to identify the warm-up period. As long as we identify the warm-up period, then the rest should be simple. Let me stop here. Then we can try the next time where in the run setup, we can define the warm-up period like 2 days, all right, and still the replication length is 5 days. So when we're doing like this one, Arena only collect the statistic and the result in the report is from the statistic collect from day 3 onwards. So we only have 3 days for data collection, day 3, day 4, and day 5. Okay, and if we also request 10 replication here, right now we use the truncated replication method for analyzing this statistic simulation. Okay, so I will run this one and see the report. All right, you look at here, we have the average and the half width here. The half width here is 6.51. Okay, take note this one. 6.51. And the average is 16.39. Right. If we don't indicate the warm-up period, what happened? Right. The half width is 6.51. Let me run again without the warm-up period. Okay, this is without warm-up period. Okay, the half width is 4.42. It's smaller, right? You wonder why? When we don't identify any warm-up period and we ask it to run 10 replication, 5 days per replication, the half width is smaller. Then we run also 10 replication, 5 days but with 2 days warm up. The half width increased to 6.51. Any wonder? It's just because of the number of data available. When we choose the warm-up period, we already remove the data for the first 2 days. All right, so basically we only have 10 replications. So fewer replication, wider the confidence interval. All right, wider the half width will be larger. So that is normal. Now let's say if we do the single batch, what happened with the single batch? Okay, okay, let's try to set up with a single batch. Let me open another file. All right, so in this case, in our run setup, we only run one replications. Okay, the warm-up period still 2 days. All right, and we run very, very long. Okay, the replication length is 50 days. All right, instead of 10 replication, 5 days, we run one replication and 50 days. Let's run it. Right, let's look at the result. All right, so in this case, Arena still able to give us the half width of the total width. Okay, and the half width is very, very small here. All right, and the way it's come up with the half width calculation here is by batching. All right, it will divide it, the data it collect from the 50 days of one replication into batch. All right, and then consider each batch as one replication. So this one is automatically done in Arena. But let's say if you want, for some reason, you want to do it manually because you want to set different confidence level, for example, you still can do it with the output analyzer. Okay, for the output analyzer, you still can go to the output analyzer and choose the function batch or truncate. All right, and the way you want to truncate, the way you want to batch, how many batch you want to use. All right, but I think we won't need this one. We just let Arena choose the number of batch automatically is good enough. All right. Any questions so far? Let me check. Okay, I have one question about the project. Okay, so the question right now is, you already collect the data, but how do you know which distribution to fit the model in Arena? Okay, cô trả lời cái này bằng tiếng Việt nha. Alright, cô assume là tụi mình đều đã biết sử dụng input analyzer để analyze data rồi đúng không? Cô đã demo cho lớp về cách sử dụng input analyzer rồi đúng không? Rồi. Khi mà mình vào input, thứ nhất để sử dụng input analyzer là mình phải chuẩn bị một cái file data dạng ASCII ha. Khi mà mình collect data thì mình đã để vào file Excel để mình xử lý data cho nó dễ. Nhưng mà muốn đưa vào input analyzer thì mình phải đưa raw data vào thôi. Chỉ có data thôi chứ không có chỉ có một loại data mà mình muốn phân tích distribution vào cái file ASCII đó, rồi mình vào input analyzer. Thì tụi em có thể chọn fit all trong input analyzer. Tôi tắt thử cái này. Rồi. Input analyzer. Khi mà mình đã có sẵn một cái file data, ASCII data, thì mình chỉ cần bỏ vô. Thì tụi em, nếu mà mình không biết distribution nào thì tụi em có thể chọn fit all ha. Rồi khi mà fit all thì tự động nó sẽ recommend mình cho một cái distribution nào đó, và mình có thể copy cái này vào vào cái arena của mình. Tuy nhiên cái mà như vậy là mình về cơ bản là kiểu nào thì mình cũng làm được, nhưng mà khi mà mình làm như vậy thì tụi em phải kiểm tra. Thứ nhất là kiểm tra hai cái thứ nhất là nếu mà mình sử dụng cái mà recommend by arena, cái distribution này rồi, thì nhìn vào cái p value của từng cái test coi nó có đủ lớn hay không. Cái p value của cái test nè, nó có lớn hơn cái alpha mình chọn hay không. Ví dụ alpha mình chọn là 0.05, nó lớn hơn thì nó là đủ tốt. Rồi, cái thứ hai, giả sử như là có nhiều cái distribution mà mình không có quen thuộc, thì em có thể đọc lại trong sách chương 9 để xem. Có một cái bản sách của cuốn textbook của mình là cuốn của Cherry Bank ha, chương 9. Nó có một cái bản tóm tắt lại từng cái features, từng cái đặc điểm của cái distribution ứng với cái tình huống nào. Rồi, những cái mình đã học là những cái rất là typical, là những cái mà tụi em cũng sẽ hay gặp, là thường là tụi em sẽ phải collect inter-arrival time, đúng không? Bạn nào cũng sẽ collect inter-arrival time hoặc là number of arrival. Thì cái đó là mình sẽ nhìn vào Poisson hoặc là exponential. Có thể là cái input analyzer nó sẽ không propose, nó không suggest cho mình exponential cho cái arrival time, bởi vì nó sẽ cứ căn cứ vào cái nào mà cho cái, nếu mà mình nhìn thử fit all summary ha, thì nó sẽ cho mình, nó sẽ sắp xếp theo mình, cho mình theo cái square error, cái nào là nhỏ nhất thì nó sẽ recommend thôi, chứ nó sẽ không căn cứ vào ngữ cảnh. Thành ra nếu mà ngữ cảnh của mình là inter-arrival time, mình học là exponential, mình nhìn vào đây mình thấy exponential, giả sử cái square error nó cũng đủ tốt, và mình nhìn vào cái giả sử mình nhìn vào từng cái kết quả của từng distribution ha, mình nhìn vào cái p value của nó. Ở đây p value nó là nhỏ hơn này nè, nhỏ hơn không phải nhỏ hơn alpha là không tốt, nhưng mà nếu mà mình vẫn được cái p value lớn hơn alpha thì mình vẫn có thể chọn được cái exponential nếu mà nó đúng với cái ngữ cảnh của mình, và cái alpha nó cái p value nó đủ lớn hơn cái alpha, thì mình vẫn có thể chọn được ha. Như vậy là mình sẽ cân nhắc hai yếu tố. Yếu tố thứ nhất là cái ngữ cảnh mình biết, cái thứ hai là cái p value nó có lớn hơn cái giá trị alpha mình chọn hay không. Rồi, còn nếu như cái ngữ cảnh, cái data mình chọn, cái ngữ cảnh nó không có, nó rất là general, nó là một cái process bất kỳ, thì tụi em có thể chọn theo cái recommend của arena cũng được, nhưng mà vẫn phải check cái p value nha. Và tự vì cái mà thường là nó sẽ suggest cho mình là gamma hoặc là beta hay gì đó, tại vì những cái distribution đó nó có rất nhiều parameter, và nó có thể adjust những cái value của parameter đó để nó cho fit nhất cho cái data của mình, nó sẽ dễ fit hơn so với những cái distribution khác. Thì tụi em vẫn có thể chọn nó nếu như mà ngữ cảnh nó rất là general. Hoặc là mình có thể hoàn toàn có thể chọn triangular cũng được, nếu như cái process của mình nhìn vào mình thấy nó khá là đơn giản, và mình muốn manipulate cái thông số của mình dễ hơn sau này, thì mình có thể chọn triangular hoặc là uniform nếu mà mình test mình thấy nó vẫn ok ha. Thật ra là nó chỉ có vài cái distribution thôi tụi em. Còn nếu mà trong trường hợp tụi em xài những cái distribution phức tạp, gamma beta vẫn được thôi, không sao hết, nhưng mà phải check p value. Rồi, các bạn nào có câu hỏi gì không? Có câu hỏi gì khác không? Rồi, ok, nếu không có câu hỏi gì khác thì mình ngưng tại đây ha tụi em ha. Tuần sau mình sẽ có cái mình là bữa cuối cùng chứ, tuần sau là bữa cuối cùng cho tụi em. Cô có thiếu lớp bữa nghỉ lễ nào không ha? Rồi để cô kiểm tra lại. Ok, so we stop here class. Về có một bạn hỏi về validation thì mình nên làm như thế nào? Về validation thì mình thứ nhất là tụi em phải chọn một cái khoảng chừng một hoặc là hai cái output quan trọng nhất. Hai cái output này là đối với mình là nó quan trọng, nó có ý nghĩa quan trọng, và cái thứ hai là mình có thể đo được từ trong cái thực tế. Tại vì validation là mình phải đo giữa cái thực tế với lại cái output của cái simulation của mình, đúng không? Rồi sau khi đo được cái thực tế và lấy được từ trong cái simulation thì mình sẽ so sánh. Tụi em có thể chọn giữa cái sử dụng hypothesis testing là tụi em làm cái làm cái t-test. Nếu mà trong arena, nếu mà tụi em đọc arena output thì tụi em sẽ trích ra được cái average nè và cái half width. Từ cái half width là tụi em có thể tính ra được cái S, cái standard deviation, nghĩa là standard deviation và average là của cái output đó trong mô phỏng là mình lấy ra được. Rồi xong rồi mình sẽ dùng t-test để mình test, mình so sánh với lại cái output mình đo trong thực tế, cái hai cái đó có giống nhau hay không. Rồi đó là cách thứ nhất. Còn cách thứ hai là từ trong arena mình sẽ nhìn vào cái confidence interval của cái input, của cái output đó. Rồi mình sẽ sử dụng phân tích những cái scenario mà mình đã học đó để mình so sánh coi là mình sẽ accept hay là reject model của mình, hay là mình cần thêm replication để mình đi đến kết luận. Em hiểu không? Nghĩa là thứ nhất phải chọn, mình phải nhìn vô thông số nào. Thông số đó thứ nhất là phải có ý nghĩa quan trọng, và thứ hai là phải đo được trong thực tế và lấy ra được từ mô phỏng để mình so sánh giữa thực tế và mô phỏng. So sánh giữa thực tế và mô phỏng thì bắt buộc là một là mình sẽ dùng hypothesis testing, mình so sánh hai con số với nhau. Rồi hai là mình sẽ sử dụng confidence interval từ trong cái mô phỏng để mình xem coi mình so sánh với lại cái ngoài thực tế mình đo được, coi mình accept hoặc là reject. Cả hai cái tụi em đều phải lưu ý là phải xem cái số lượng replication khi mình run cái mô phỏng của mình có đủ hay không. Nếu mình chọn waiting time, tụi em có thể chọn waiting time của nếu mà chọn waiting time của từng cái queue thì cũng được, nhưng mà nếu mà em có nhiều queue quá thì nó sẽ phức tạp hơn, đúng không? Nếu mà waiting time của từng cái queue của đối với em là quan trọng thì em có thể chọn cái đó, nhưng mà nếu mà nhiều queue quá thì mình sẽ mệt hơn, hoặc là em chọn một hoặc là hai cái queue quan trọng, hoặc là em chọn time in system thì nó sẽ bao gồm hết tất cả các queue luôn. Nghĩa là càng nhiều out, càng nhiều cái so sánh thì đương nhiên là nó sẽ càng chính xác, nhưng mà khả năng là phức tạp nó cũng là nhiều, và khả năng là sẽ có những cái mà nó sẽ không match lắm. Thì lúc đó mình phải quyết định coi, phải xem kỹ lại model hơn. Còn cô khuyên là mình chỉ nên chọn một vài thôi, khoảng chừng hai cái là được. hai cái quan trọng nhất mình muốn so sánh là được. Còn sau này làm thesis thì nó sẽ phức tạp nhiều hơn. Rồi, còn bạn nào còn hỏi câu hỏi gì nữa không? Rồi, nếu không có thì mình tạm dừng tại đây ha tụi em ha. Rồi. See you next week class. Tuần này mình sẽ không có lớp lab nha. Nhưng mà tuần tới thì cô nghĩ là mình sẽ có một lớp lab online cuối cùng. Chắc là sẽ không offline được nữa rồi, thành ra là sẽ có lớp lab online tuần sau nha tụi em. Rồi, cô sẽ thông báo, cô sẽ confirm thông báo lại trên Blackboard nha. Rồi, nhưng mà trên tinh thần là tuần sau mình sẽ có một cái online lab vào thứ Tư và thứ Sáu. Ờ, Cuối tuần này thì mình sẽ biết là thi như thế nào. Tại vì trong tuần này thì trường mới có một cái cuộc họp để quyết định là nên thi như thế nào. Nhưng mà hình như cuộc họp đó là ngày mai hay là ngày mốt gì đó. Ra cuối tuần này mình mới biết. Là đầu tuần sau thì chắc là cô sẽ thông báo được với lớp là mình sẽ thi như thế nào. Rồi. Ok. Bye class. Rồi, tạm biệt các em ha.
Recording stopped.